The DCB parameter represents the data attributes. And this is where we are going to assign things like our logical record length, our record format, our block size. And these are all exactly the same attributes that we had seen in the TSO ISPF module relating to allocation. These are exactly the same values that we are going to be using. So depending on the data set type that we are creating, we're going to specify those same attributes here. In addition, you can see we have a refer back option that we can use, as well as a dataset name option. Now, the dataset name is curious because of the fact that we can code a dataset name that has the attributes that we are interested in, and then they will be copied from that dataset and assigned to the dataset that we are creating. So it becomes a shortcut way of being able to create a dataset based on the model of another dataset itself. So the characteristics are going to relate to the record formats themselves. And again, we can go ahead and use that dataset name to copy characteristics, or we can refer back to a previous coding in our JCL. One other point to remember is that with the DCB, the subparameters like logical record length and block size and record format, these have all now been modified so that they can be actually coded as separate parameters so that you do not require the DCB parameter. As such, these subparameters like block size, logical record length, record format, and dataset organization, and all the other valid subparameters under the DCB, they can be coded as separate keyword parameters in your JCL. So it's just another option that provides some flexibility in how these different values can be coded or specified. The space parameter allows us to determine now how much space do we want for our data set. And there are a variety of ways in which space can be assigned. Again, we have talked previously about the role of tracks and cylinders and blocks. We can specify a primary quantity, we can specify a secondary quantity, we can specify directory blocks if we are allocating a partition data set. We can indicate whether we want space released or whether we want contiguous allocation. All of these provide a way for us to be able to identify how the data set itself, space, is supposed to be assigned. So basically, within the cylinder, track, or block, this is going to represent the physical space where we obtain our primary allocation. In other words, how much space do we want to begin with? And then we can optionally specify a secondary allocation, which allows us to grow this data set in the event that our initial estimate was too low. We can specify directory blocks if we want to use this method for allocating a partition data set. And then, of course, release to release unused space, contiguous to request that our allocation occur in one big piece, and then rounding, which is where when we specify a block, we get it rounded to a cylinder boundary. Now again, all of these are going to simply be contingent on roughly how big do we want our data set to be. And as a normal matter of course, what you're going to be looking at here is going to be things like, if you're creating test data, for example, you may just venture a guess as to how much space you need and try it out. If the data set is too big, well, nothing really lost. You can always specify the release parameter to release unused space. In addition, if it's too small, then your program will eventually terminate abnormally, and you go ahead and increase your allocation size. For testing purposes, this is a perfectly acceptable way of finding out if you're not sure how much you're going to be working with. In addition, storage administration policies often come into play by going out and releasing unused space as a part of a normal system process that runs. And so the idea of really being very tightly managed is kind of fallen by the wayside. So it's not quite as important anymore that we be quite as accurate about our space allocations in this. When it comes to production data sets will normally be allocated by the storage administrators whenever a work is ready to go into production. Since they are the ones that are going to be managing it, they will designate the volumes that they want to place that data set on, as well as working with security to ensure that the right rules are built for who has read and write and update access to that particular data set. So again, from a space allocation perspective, just as a reminder, a track represents the amount of data that we have in one rotation of a disk surface. A cylinder represents all of the tracks that are directly above and below each other. In the case of the 3390 device, we are looking at 15 tracks being equal to one cylinder's worth of space. Each track having about 55K worth of data available to it. And so what we would normally do is that we would allocate the amount of space based on the size of the records, how many records we can hold per block, how many blocks we can store on a track, and then how many tracks we need in order to hold the data that we intend. One cylinder allocation is not a very large allocation. And so even if you're dealing with several thousand records, allocating a couple of cylinders for a data set is not a big allocation request. And so for the most part, even if you're wrong by 100%, it is not going to be a big factor in terms of space waste. Now, in this example of referbacks, what we are seeing then is that we are seeing a DD statement, tlib vol, that contains a DCB definition. Notice that there's no dataset name or anything associated with this. But then when we look down, we see that there are two DD statements below that refer back to that particular DCB. And you can see we have the DCB coded there as an asterisk.tlib vol. This is the type of role that a referback provides in giving a backward reference to a previously defined statement. Now, in general, this can come in handy when you have a lot of definitions and you want to refer back to something that is common that everybody can refer back to and make sense of. However, as a practical matter, referbacks are not used very often except in very special situations like this. The reason being is that when we actually get involved in jobs that have multiple steps, when we may have to restart the job and we may have to perform other actions in order to bypass certain steps or to perform other functions, the referback approach can fall apart. So in other words, if we bypass a step during restart, the referback will not work. And so as a general matter, of course, we'll find that referbacks are not used very frequently in production JCL or in any work that potentially could be manipulated to have to eliminate steps or bypass steps in the event of reruns. So the referback has a very specific role. It can be useful, but it is not going to have widespread usage.